Right, start with linear search. It's the simplest search that we can do. Okay? All we're going to do is we're going to just look from the first element, element 0, and we're going to compare each item we look at until we find the one we're looking for. Okay? The best case scenario, when linear search is quickest, is it the first thing we look for. Not very likely. Okay? The worst case scenario is we look at every single item and go, oh, the thing I was looking for didn't exist. With a small list of numbers or data values, whatever you're looking at, it does not take very long to process. Okay? So if you're looking for situations where linear search is better, it's got two advantages. For small data sets, it is quick. Particularly if you start thinking about how the CPU cache works. If this is held in the CPU's level 1 cache, it's going to be blindingly quick to search this. Quicker than any complicated methods. Even if it was quite large, you know, maybe 50, 100 items. If it was in the CPU cache, you could access that blindingly fast. If the data structure gets larger and it won't fit in the cache, then obviously the advantages of that disappear quite a lot. The other main advantage of this over any other search methods, it can search data that's not in order. Okay, so if you know you've got data that can be randomly spread, like the data I've drawn here, you cannot use the other search method, binary search, because binary search only works with ordered data. Okay, so quite a simple process. So we just go, is that the one I'm looking for? So if I was looking for 9, I'd look at 4, I go, right, increase the index, look at 17, no, look at 3, no, look at 9, stop. Okay, and say we found it at position index 3, and that's what we probably return. Remember what we're searching, we're not just mindlessly searching numbers, these are probably identifiers for data in a structure. Probably a hash table maybe, so that if you then hash that number, that you know it exists and you can find the data, or it might be an index for a big database structure. Okay, in reality we don't spend our time writing algorithms just to search lists of numbers for no good reason. Okay, it's an exercise based thing. Now there is an optimization you can do with linear search if your data is in order. So let's just have some ordered data. And 1721. Okay, let's say it doesn't make any difference. It's the same process if the data item's there. Start at the first item, as soon as we get to it, stop. But if it's in order, let's say we were looking for 10. Because we now know something about the data, there's some structure to the data that is in ascending order in this case. If we look at the first data item, we say, oh, 5, yeah, okay, it's not that one. Look at 9, oh no, it's not that one. Look at 11, we say, oh, it's not that one, but that number's bigger than the one we're looking for. Because they're in order, we can go, oh, hang on a minute, if that one's bigger, that means the next one and all the others are going to be bigger. So there is no point in searching further. Okay, so that's a nice little optimization you can do on linear search if the data is in order. So sometimes you may get a situation where you've got ordered data and you think, oh, I want to search it, binary search, that's the best. But if it's just a few data items, it's actually quicker to just add one to an index. That's the quickest operation inside a CPU, to increment a register. There isn't quicker operations than that. Okay. Bearing in mind, if you're going to compare it with binary sort, you've got to do some calculations, which obviously we'll talk about in a sec. Okay, so bog standard linear search, very easy to implement. Just have a while loop, and that's it. Okay, so let's talk about binary search. So the caveat for binary search, it only works if your data is in order. Now there have been questions on papers before where they said, here's some data, we binary searched it and we got this number. Or we didn't find a data item. because it wasn't in order, and you have to explain why. Okay, so be careful that they might do things like that. They may give you situations where an algorithm they suggest is not suitable for what you're trying to do. Okay, so binary search. This all hinges, it's a divide and conquer strategy, okay? So it all hinges about throwing data away. We don't want to have to look at everything. That's what all divide and conquer strategies do. Okay, they simplify things. So in this example, we've got 6 data items. They're at those indexes, 0 to 5. And binary search is all about halving your data, the size of it. So every time you examine a piece of data to say, is that the one we're looking for, we can hopefully discard half the data set. Okay, so if we start with 10 million items, after looking at the first item, we should be able to say, you know what, I started with 10 million, but I can discard the 5 million of those. So I've only got 5 million to look at, and then keep halving. So it's a really good algorithm. So first off, we've got to find where the middle value is. So if we start off and mark the ends of our data as left and right, to find the midpoint, all we've got to do, add those two values together and divide by 2. What we must make sure when we do the division is we do what type of division? It's got to be integer division. You can't have index 3.5. Alright, wouldn't make any sense at all. Luckily, inside a CPU, divided by 2 is another super quick operation. It's actually just a shift. If you shift the bits to the right, so if we had a bit of binary, what number is that? It's just a unsigned number. 4. Yeah, everyone happy with it's 4? If I shift it that way, one position, what number do I get? 2. That's a quick operation. So division by 2 is quick. Addition of 2 whole numbers, integers, is quick. So even though this looks like, oh, there's quite a bit of maths involved, not much, but it is still going to take longer. There's 2 operations rather than incrementing, which is what you do with the linear search. Okay, so we find the midpoint. Because we're doing integer division, if we just look at this one as an example, we end up with 5 divided by 2. So when we do integer division, we're going to get 2 as our answer. So we're going to say that's the middle value. There is no middle value because we've got an even number, but it doesn't matter. So if we're looking for 9 in this case, and we say, right, at the middle, what is the number? It's 11. Okay, well that isn't what we want, so we can't stop yet. But we know, because this list's in order, that all these data items are pointless looking at. So we're going to discard that half of the list. So we go bye-bye. So we need to move this pointer in. That's how we do the discard. We don't rub them out or anything like that. We just move this pointer. So we just say, right, okay, well if that's where the middle value is, we want to be middle minus 1. So the only thing about this algorithm is remembering that. If you want to go to the left of something, you take 1 off. If you want to go to the right of something, you add 1 on. Okay, and then we just binary search this part. So we end up with 1 divided by 2 when we calculate the middle. Well, that's, with integer division, is going to give us 0. So we look at that one and we go, oh, that's not the one we want. But 5 is smaller. Let's discard that part of the list. Well, there's only 1 item in it, but we're going to do the same discarding. So we're going to say +1 for the left. So the left moves across. Okay, so now the only one we've got actually there is 9. So when we do 1 plus 1 and then divide it by 2, we get 1. And that's the data item we were looking for, so we can stop. Okay. So if we was to linear search that, it would be quicker, looking for 9, because we don't look at 2 items. We have to look at 3 items for the binary search. So when we've got a small data set, binary search is slightly overcomplicated. There's some calculations to do, there's some movement of pointers to do, and there's a loop to do. Whereas with linear search, you've got a loop, yes, and you're incrementing a pointer. There's not much going on. I often find that when I'm doing something and I need a search algorithm and I'm not doing high level code, that the first algorithm I'll knock up, because it's easy to write, is a linear search. And then you go, well, that's not very quick, I'll do a different method. Okay. So they've both got strengths and weaknesses. Binary search, because its time complexity is quoted as n log n, as you add more data items, it doesn't have that great an effect on its performance. Okay, so if every time we double it, it actually only means we only have to look at one more value. It's a cracking algorithm, binary search. You've got to have your data in a structure that allows it to be searched though. So that's either a linear sorted array or a tree structure. So if you've got a complex data structure, if it's in a binary tree format, you can still do binary search. Okay. Right, I'll stop the vid there and then I'll talk about these sorting ones.